We are in part 12 of a unit on comparing and contrasting linear and exponential functions. We've been looking at exponential functions recently, and we'll continue doing that in this video. We've been focused on symbolically representing how those exponential functions changed and trying to understand that symbolic representation visually with Mathematica, this program here, especially a command called manipulate, which makes animations. In this video, I'll introduce you to another Mathematica command called grid, which does make grids or matrices of, well, they can be numbers, they can be letters, they can be graphs even that are included in the grid. I also want to verbally try to correct some mistakes that I made in the last couple of videos. I did make some annotations in those videos to visually correct those mistakes, but I want to verbally emphasize how to correct those mistakes right now. Essentially, I used the wrong kind of phrasing. I used the phrase relative rate of change when I should have just used relative change. Okay, get rid of the words rate of. Just call it a relative change or a percent change. No rate of. That'll be for later. Alright, before we get to the main math, let's focus on the syntax for grid and see what it makes. Again, it makes matrices. It makes arrays, you could call them. For example, if I want to make a 2 by 2 matrix where the letters A and B are in the first row and the letters C and D are in the second row, this is the syntax. There you have it. No parentheses, that's okay. It is a 2 by 2 grid. If I want to make a 2 by 3 matrix, 2 rows and 3 columns where I have A, B, C in the first row and D, E, and F in the second row, this is the syntax. And for example, if I want to make a 3 by 3 matrix where now the third row is consisting of G, H, I can do that. I can even make grids within grids, matrices within matrices. For example, I can replace this I with a grid. Let's make a 2 by 2 matrix in place of I where I have U and V in the first row and W and X in the second row. There we have it. This 2 by 2 grid is the lower right corner of the overall 3 by 3 grid. Hopefully that's pretty clear. Alright, on to the math. Here's the example we've been looking at recently. We fit all these points to with an exponential function. What function? Right down here, 3 times 1.2 to the x. And then using that particular example, we tried to get a symbolic representation of how delta y depended on delta x. We imagined x starting at a value x, changing by an amount delta x, and looking at how the change in y is affected by that. It was fairly complicated, more complicated than for linear functions. But we made it a little simpler by dividing everything by y, or f of x, to get this equation. And here's where I made one verbal mistake. I called this a relative rate of change. Okay, I should have just called it a relative change, percent change. Both of those are percentages, by the way. Relative change and relative rate of change here in this case, because of the word relative, could be thought of as percentages. But because I'm not dividing this all by delta x, I really should just call it a relative change. All right? Let's go down and look at the animation we created to understand that equation. Again, rewritten right here. Here's the animation. Manipulate, show, combine to make an animation. A is the animation parameter. It's the starting value of x. It is x, so to speak. Delta x I'm keeping fixed in this, and it's fixed at 5. What do we see? We saw that no matter what A is, ultimately, the relative rate of change, or the relative change, excuse me, was the same. In this case, if x is negative 2, the starting value of x, and delta x is 5, so that I increase x from negative 2 up to 3, delta y is the length of this red line, and y itself is the length of these vertical blue lines. And what did we get for the value of that relative change? Both by actually calculating as delta y over y, and as calculating as 1.2 to the delta x power minus 1, again delta x is 5. In both cases we got 1.48832. What does that mean? One thing I said correctly in a previous video is that the length of the red line, which is delta y, is about 48.8% more than the length of these vertical blue lines. That is true. The length of the red is longer. It's close to 50% longer. One thing I said incorrectly was I said the relative change in y, okay, I think I put rate of in there as well, but the relative change of y was about 50%. That was wrong, okay? Y is more than doubling. Y is close to 2 here, and it's over 5 there. It's more than doubling. It's growing by over 100%. In fact, it is the relative change of Y as a percentage. It's this number. It is 148.8%. That's the relative change in Y, 148.8%. All right, let's do some new things now. I'm going to make this animation nicer. Oh, and again, by the way, the mathematical point of this is it doesn't matter what the starting value of x is. That red line is still always about 50% longer than the blue line, the vertical blue line, no matter what the starting value of x is. It would be nice to include delta x in this animation. I fixed delta x at 5 before, but let's include it as part of the animation. And the syntax I'm showing you right here will create delta x as another slider. You can see it's still within the manipulate, but outside the show. By putting a 5 in here like this, that's going to start the value of delta x at 5, just like it was before. But this is going to allow me to go as low as 0.1 or as high as 7. Let's enter this. All right. Hopefully you understand, though, that if I move the slider, nothing will happen. Why? Because there's no delta x's up here within the show. Remember, 5 is the delta x from before, so what I need to do is I need to replace all those 5s with delta x's, which I'll do right now. Hopefully I don't forget any. I think that's all of them. Yes, now I can see the change in delta x. Delta x itself is changing. Okay. It would be nice to make this even more ideal to see the value of the relative change, either as delta y over y or as 1.2 to the delta x minus 1. What is the relative change? It would be nice to see that in this picture. That's where grid comes into play. I'm going to put the grid around the show, but still inside the manipulate. Make sure you get these things in the right spot. The square bracket does end the grid, these curvy braces and the other curvy braces. The show part, the graph, is essentially going to be an entry in a matrix. Let me enter this as is. When I do that, though, I do see the downside of the graph is made smaller. That can be fixed, though. You can do image size still within the show. Arrow medium will make it nice. There we go. Alright, what am I going to put in the rest of the matrix? Well, I'm going to put another matrix, a grid within a grid, a matrix within a matrix. So in the second entry, after the comma there, I'm going to use grid again. And I'm going to put initially at least a 1×3 matrix in here. The first entry is going to be the letter A, but I don't want to just type an A because that's going to be a number for the animation parameter. So what I'm going to do is I'm going to type text and then in square brackets put an A in quotes like that. That puts an A in there. There we go. There's the A. The first entry of this, the big overall matrix, is this. The second entry is this. I think I'd like a little bit more space between those. I can put some commas in here, essentially making my matrix wider. There we go. Now A is more spread out. I like this A to be bigger as well. There, it's nice and big. I'm going to put an equal sign next inside here. And evidently you only need quotes around it. Evidently you don't need the word text, the command text there. I was copying this from somewhere else. Maybe that works with the A as well. I didn't try it. Make that bigger. There's a bigger equal sign. And then let me put the letter A without quotes there. That's going to be the number A, starting at -2. How can I make that bigger? I can put that within a style and put the word large after it. There, now the number's bigger. Okay, so as I change A, I can see its value change over here. It would be nice to also see delta x change. So I'm going to copy and paste this to make my grid within a grid be not just a 1×3 matrix, but a 2×3 matrix, and I'm going to replace this A with delta x and this A with delta x to see the value of delta x too. So I can change both A and delta x and see their values change over there, not just up here. And finally, the best thing to have would be the value of 1.2 to the delta x power minus 1, representing the relative change of y. Alright, so again, let's do a copy-paste. I'm essentially making a 3×3 subgrid within my overall grid. Replace this delta x with 1.2 to the delta x power, then minus 1. Make that bigger. Change this as well to give that value, 1.2 to the delta x power, then minus 1. There we go. That's pretty nice. Now we can see there's the starting value of a, and delta x is 5, and I get the same value for that relative change of y, again representing a relative change of 148.8%. It is not affected by a. A changing doesn't affect it, but delta x changing does. And for example, if delta x is small, like less than 1, now we get this value, so that would mean the relative change of y is 16%, almost 17%. Rounded to 17%. You can't even see the red line anymore, hardly. It's about 17% as long as these vertical blue lines, and it doesn't matter what a is. Now you can see it better there. That vertical red line now is about 17% as long as these vertical blue lines. Again, I could change delta x to change that value, but the interpretation is always the same. Okay, one more time with this example now. The relative change of y is 16%. This vertical red line is 16% of the blue line. It's shorter. It's close to 84% smaller is another way to think of it. Think about that, look at the code, and with that I'll end this video.